Okay, so we're going to go over LIGA, micromachining. Now, you already had some of that, right, in the overview section? What do you remember what LIGA is? What does LIGA stand for? Come on, wake up.
Long attenuated German acronym.
Close. Long involved German acronym. That's one definition. I actually heard that at Sandia National Labs. Long involved German acronym. Long involved German acronym. Right. So it's basically what? What does it entail from what you remember?
Electroplating?
It has electroplating in it.
You pattern a piece of the PMMA electroplate using that as your mask, as it were, and then it also sort of you use that as a sort of mask mold combination for your electroplating, so that you end up with the finished piece.
Okay. So that's good. So you're going to illuminate PMMA, which is polymethyl methacrylate, or plexiglass, right? You're going to illuminate that, and then you develop that out. Where you have your openings, that's where you're going to electroplate into with a metal. They use nickel a lot. Nickel's really good for the electroplating. And then after they electroplate it, then they can remove the PMMA, and then you either have a stamp, so you can use that metal part to stamp out things, or you have a part that you can use directly. Okay. So there's lots of different ways to do that. Uses. Okay, so here we see a picture of a LIGA device, produced device. Now again, this is lithography, Galvanoformung, which means electroforming or electroplating. Okay, one of you pointed that out in the crossword puzzle. You did, yeah. So I've got to fix that, because electroforming and electroplating work in the crossword puzzle, the LIGA crossword puzzle. So, and they're both pretty much the same thing. So thanks for pointing that out. And Abformung is the molding part. Okay, so this was developed in Germany, and then of course a lot of other places are using LIGA now. Okay, Sandia National Labs does a lot of LIGA out on the West Coast, and the guy who developed the LIGA process, the high aspect ratio microsystems technology process for Sandia, is Todd Christensen, who you saw at Manufacturing Day, who started his own company. Okay, he's an expert in LIGA. So that's why if you want to work for Todd, you probably should really learn this LIGA stuff and then go to his website and go through everything that you can find about his process on the website, and then maybe also do some Googling around. Now we used to have some really thick textbooks back here by Madhu and stuff. I hope they're still around, and there's a chapter that Todd wrote. So if you're going to try to get a job somewhere, you try to do some background stuff. Don't pretend you're an expert on LIGA, but just make sure they understand that you know something about it and you find it interesting, and then they see that you're interested in the topic and you're willing to learn more. So if we look at this this image here, this is really cool. What do you see here? I mean, what's different about this than some other type of lithography that you might do, or structures you might do? They're tall and thin. What else? They're at angles, right? Do we do that in lithography? They're usually straight up and down, right? So how do you think they made this? This is actually, just to let you know, this is a scanning electron microscope picture. Okay? Let's see, is there any scale on this? No, there's no scale on it. It's a scanning electron microscope picture. These are copper, I believe, or maybe nickel.
Did they make
some metal.
And then fill it?
Yeah, they made a mold and they filled it, right? Here's your base plate. Okay, so this is a conductor right here on the bottom. So they electroplated into these holes, right? And then they remove the stuff around the holes, which now has posts in it. And they probably polished why the top is flat. So you electroplate in, you polish it down, then you remove the PMMA. But how do you get angled structures? And two sets of them. You got this angle and you got this angle. How do you think they did that?
PMMA at an angle? They exposed it at different angles?
They exposed it at two different angles. Okay, so they did a double exposure basically. All right, and then you'll find out with LIGA, use X-rays. Right, the X-rays go in a very, very straight line. So when one exposure, they had a mask with holes in it, right? So the holes in the mask allow the X-rays to go through, and they go in this direction. And then they rotated the sample and maybe put a different mask in, maybe use the same one. And then they did the other direction. So that's pretty cool. Okay? So I'd like to talk about the pictures. All right, so this little lecture, which will probably end up being an hour long by the time Matt's done with it, we're going to talk about X-rays. We pattern polymethyl methacrylate, that's PMMA. They also use something called SU8, which is a very thick resist. So some people use SU8. Okay, so we're going to go through this lecture, and this will tie into a lab you'll do down. Okay, so you'll be able to compare and contrast the real X-ray LIGA with the simulated one you're going to do in the lab. So again, LIGA is a German acronym for X-ray lithography. So it's X-ray lithography, electroplating, and molding. Okay, so if you look at this picture, this is a LIGA gear. Now, of course, these bearings in here isn't part of the LIGA process. So they made the gear, and then they dropped the bearings in. All right, so this was probably a proof of concept device they made early on. If someone could close that door, that would be great. Thank you. Okay, so when did all of this start? Back in the 80s? And they did it in Karlsruhe, which is a place in Germany. It's a nuclear research center. Okay, they developed LIGA. All right, so it allows you to make high aspect ratio microstructures. So what's high aspect ratio? What is aspect ratio?
A ratio of the height of an object versus the width of the object.
Height over width. So if it's tall and skinny, will that number be high or low?
High.
Great. So we want to make tall, skinny structures. It's hard to do with normal light, right? Because the depth of focus, like in a stepper or in a 1x contact printer, might only be a micron or half a micron. You know, maybe 2 microns if you're lucky, right? Because the depth of focus for optical stuff usually looks like this. So if you're trying to image a structure and you look at it from the side, right, this is the best focus right here. But if you move up and down from there, the focus goes out either way. And kind of think about that. If you have a magnifying glass, right, you put your back to a window and put a piece of paper between the put a piece of paper, have the magnifying glass between the paper and the window. You can image your window on the piece of paper, right? You should try to do that. Okay, what happens when you move the paper? It gets fuzzier, right? It gets out of focus. The more you move the paper, the more out of focus it is. So now try to turn that on its head. You're imaging photoresist, and your wafer moves up and down, right? You'll be going in and out of focus, right? Now think about looking inside the photoresist. Okay, so you've got some photoresist here. Your image will not be focused all the way through. There'll be one place that'll be best focus, and everything will be a little bit out of focus. Well, with photoresist, it's not a big deal. That's what, a half a micron to a micron thick, typically. Now, the thick photoresist we used in the fab, 6 microns. It's the thickest you'll ever use. Okay? So, yeah, the depth of focus may not be as big of an issue. But let's say I want to I want to image something that's 100 microns thick or 500 microns thick. I'm going to make something in PMMA that's a half a millimeter tall, but maybe only 2 microns wide. You can't do it with light. You have to use a different type of light, not visible light. Okay, so you use X-rays. Okay, and you use X-rays coming from a synchrotron radiation source. That's pretty cool. Okay, these structures like the ones you see here. So let's take a look at each of these. This is really tall and skinny, isn't it? Okay, these are probably maybe 10 to 20 microns wide. Okay, so if that's true, they're about 100 microns tall. Say they're 10 wide and 100 tall. What's the aspect ratio? 10 to 1. Let's say it's a millimeter tall and only 10 microns wide. Then what is it? What's a millimeter in microns? Come on. 1,000? That's it. Millis, 10 to minus 3. Micro is 10 to minus 6. Yep, 1,000. So now you got 1,000 to 10. It's 100 to 1. 100 to 1 aspect ratio is pretty good. Okay, and they can do better than that. What the heck? It's telling me I have to do something tomorrow. Okay, sorry about that. So what do you think these tall cylinders could be used for? Kind of a neat device, but what do you think it could be used for? Any ideas? Why would I make structures like this?
Brushes.
A brush? Well, these are pretty stiff, usually.
Filters.
A filter. That's good. Why do you say that?
Because if you put an electrical charge on it, shouldn't you be able to catch certain particles within the little...
Yeah, so if I put some charge on this, let's say this is metal, because it usually is when you do LIGA, right? So the base plate here could be charged, or could have a voltage on it. Let's say we put positive voltages on here. Okay, then anything with a negative charge would stick to this, wouldn't it? That's one way to do it. Another way is the space in between here, these spaces, can be very well defined, very precise. So going back to your filter analogy, you can actually make a filter that's perfect, right? It has only a certain width that it allows through. Anything bigger gets stuck. All right? So you'd have to put a cap on it here, right? So the fluids or whatever you're trying to filter can't jump over the fence. But it's like a fence. That might not be a bad analogy. So, okay, so the coyote fence for really tiny coyotes. So here they're saying that it's made out of PMMA. The posts, they're 3 micron spacing and 300 microns tall. I don't know, that looks like an exaggeration. Looks like it's a lot wider than that. All right, now look at this guy. What is this? What do you think this is? What's it look like?
Spring.
A spring. They use LIGA to make watches, watch parts. Right? You make little metal parts, and, you know, they're pretty, you know, those Swiss watches that you can get, they're pretty intense in terms of the mechanical parts in there. They can't machine these anymore if they make them too small. So they use LIGA. Okay, so they actually, in Switzerland, they do some of the LIGA work there, and then they send these little parts to China for assembly. Okay, little springs go into cameras. You have moving parts now in your cell phones, like for autofocus on your camera. Some of the cameras and cell phones focus now. The first ones didn't. They were fixed focus. You know, things were generally sharp if you were about 5 to 6 feet away. Okay, if you got closer or further away, nothing was in focus. Now they focus, so they need moving parts. So you need little springs and things. So if you look at the scale here, okay, you can see it's 100 microns is this distance. So how tall do you think this is, if you had to guess?
200.
So this is twice as long as this? You say 50, you say 200. Let's close the gap. How many say 50? How many say 200? All right, this time democracy wins. It's about 50 to 75, right? So you would take this length and just lay it across here and measure it. Okay? So you need to be able to interpret these different images, right? They usually have a scale. We already talked about that. This is really cool. What do you think that is? What do you think this guy is right here?
It's fiber optic.
It's a fiber optic, right? So you guys ever play with an individual fiber optic and have to align them? Do you do that in optics, Cambies? Yeah, it's not easy, right, to align fiber. So this is a jig that they made with LIGA, and you can be precise in how you make this. And then electroplate it in, and then everything is very precise, and you just snap your fiber optics in, and then they're perfectly aligned. And they might put something in between here, I don't know what, a lens or whatever. But you can see that you can use LIGA to make jigs, right? To make optical tables, things like that. And there's a really nice part in one of the Enka videos where they talk about a micro-optical table. They have tiny lenses, they have a monochromator, you know, a grating in there, all kinds of stuff. And this thing is about 1 centimeter big, right? So very, very cool stuff you can do. So if you can make little parts, you can do a lot with it. All right. So we talked about aspect ratio. Okay, so surface micromachining the aspect ratios aren't that great. Okay, so I'm going to have you do a thought experiment. Okay, so this tooth is about 8 to 10 microns wide. So this, from here to here, the radius of this thing is what, do you think? If you had to guess. From the center to the edge. If this is 10, the tooth, how many teeth can you line up? Estimate.
100.
About 100? 80?
I'd say guess like 10.
We're talking microns or teeth?
Number of teeth.
And
Oh.
probably
About 10? 5 or 6? Well, they're about a little lower, a little shorter than the space between the holes there.
So if I were to do teeth, right, they're about that long. So I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, maybe 20-ish. So this could be 200 microns, maybe, right? Or maybe 100 microns. We can argue all day. About 100. Let's just, I'm a physicist, right? Physicists do order of magnitude calculations. So let's say it's 100 microns, the radius. So if I make this structure, okay, and it's 200 microns across, right, the diameter, okay, the thickness of this polycrystalline silicon here, the thickness of this, you can't see it, but if you were to look at it, is less than 2 microns. So let's call it 2. What's the aspect ratio of this gear? It's 200 microns in diameter, 2 microns thick. What's the aspect ratio?
1 to 50.
1 to 50? 2 and 200?
Oh, 200. 1 to 100.
1 to 100. Is that a good aspect ratio or a low aspect ratio? A high aspect ratio?
Low.
It's low.
But that might be what you want.
Yeah, well, in this case, this might be what you want, but this is a low aspect ratio. So surface micromachining is pretty low aspect ratio. Okay, so LIGA aspect ratios you know, they can be as high as 10 millimeters tall and hundreds of microns wide or tens of microns wide. So you can get very high aspect ratios, okay? In bulk micromachining, you can get fairly high aspect ratios because you're going through the whole wafer. Okay, they have something called the Bosch process, deep reactive ion etching, where you can etch very, very thin structures, very deep channels. Okay, right, you can make a hole right through the wafer, so you can make a 10 micron hole. Goes through a 600 micron wafer. Wafers are 600 microns. What's the aspect ratio of that hole? 600 deep, 10 microns in diameter. Yeah, 60 to 1, 100 to 1, on that order, okay? All right, so, you know, some structures, if you use bulk micromachining, you can get up to 100 to 1 aspect ratio. In fact, that's how they judge deep reactive ion etchers. What's the highest aspect ratio you can get with this material? So when a semiconductor company buys 400 deep reactive ion etchers to put in their mega fab, you know, they're going to want to buy ones that can get their aspect ratios that they want, right? So that's a quality metric. All right, so the LIGA process. So it's basically the same in some respect, except there's some differences, right? So the light source in our fab, what we use, our 1X contact printer, what's the light source? Do you remember? What kind of lamp? It's a UV, right? Near UV, it's blue. You can see the light, it's blue light. So it uses I, G, and H lines. So what does that refer to? What kind of lamp? Mercury arc lamp. So that's one light source we use in lithography. We use lasers, krypton, argon lasers. They're common. Now they're using those fiber lasers as light sources. High intensity, right? Well, in LIGA, we use X-rays, and we use it from a synchrotron radiation source, which is the type of light bulb. So deep UV, near UV, I should say near UV invisible, mercury arc lamp. You want to do really short wavelengths, high frequency. You want to go to X-rays, very, very short wavelengths. You use a synchrotron radiation source as your light bulb. That light bulb's the size of a couple of football fields. One light bulb. Okay? Produces light in a really cool way. So we get our X-rays from a synchrotron source, and then we can expose it, and then we can electroplate into the holes we make, and then we can use those electroplated parts either as a mold or as a stamp. So you can take your metal part and stamp it into plastic. They do that with microfluidics a lot. Types of plastics, polymers, okay? So after we expose, we develop, and then we electroform or electroplate. So this could be nickel, right? The substrate here is a metal. This is the blue stuff, or the turquoise stuff, is the PMMA, polymethyl methacrylate, that's been exposed and developed. And then we electroplate into it. So we apply a voltage here, put it into a, what do they call it, an electrolytic solution that has the ions in there for the metal that you're interested in plating, and you plate into it. Top, make it flat, that sort of thing. So we have positive and negative electrodes in our solution. We put some positive ions in there, metallic positive ions. They're attracted to the negatively charged cathode. Cathodes are negative, anodes are positive. You remember that? Did you guys learn that? Okay, good. And then the ions are attracted to where it sees metal, so it'll plate the back of the system, it'll plate into the holes. It won't plate onto the PMMA. And you keep doing that, you keep running it until you get the desired thickness you want of the metal. Okay, Pretty straightforward. After we electroplate or electroform, we planarize. So we go ahead and we polish this down so it's flat. And then the top of our gear in this case is flat. We take the PMMA off. Okay, let's zoom in on that. Take the PMMA off so it's gone, but it's still stuck to the substrate. And we can remove it from the substrate through different methods. And then we have a part. Or if we leave it on the substrate, we have a stamp. Make sense? Okay, good. See, did I leave anything off? We can use the parts by themselves, or we can leave them on the substrate. We can bond some of these different parts to other wafers. So you can do wafer bonding. Okay, and you need to do a lot of metrology, so a lot of measurements are involved with this. So the height, the quality of the material that you're electroplating in, that last. Okay, so this is an overall cartoon of the whole thing. So we start with exposing. So we've got our PMMA here. That's the turquoise stuff. We have our mask. Now, in lithography that we do in the fab, what's our mask made out of? Quartz. So clear glass, right? It passes light through, visible light, and near ultraviolet light. And quartz is clear for UV. So the 365 nanometer line in mercury arc lamp goes through quartz. Okay? You can also use soda lime. That's another type of glass, which is transparent to those frequencies of light. Synchrotron radiation, X-ray, the X-ray band from synchrotron radiation. X-rays will stop in quartz, okay, or scatter. Okay, so you can't use quartz. You need something that's clear for X-rays. What's clear for X-rays is something called beryllium. So when you look at it, it looks opaque. It's like X-rays can't go through this. But yeah, X-rays don't even see the beryllium. They go right through it. So when they make X-ray tubes, they have a beryllium window in the X-ray tube. So the X-rays can go straight through the X-ray tube wall, still maintain vacuum on the inside of the tube. Okay? But you need something that stops X-rays really well. Okay, what do you think that is? This stuff right here, this is gold. So gold is like the chrome for the optical mask. Gold is like chrome, and beryllium is like quartz. So you'll be asked to compare and contrast, right? LIGA with what you do in the fab. Okay? Good. Okay, and the resist in the fab, we call it polymethyl methacrylate or plexiglass in LIGA. We developed both of them. The chemistries are a little different. Okay, and then we electroplate into the mold, planarize and release the part. So that's the overall process. Those are the basics of the process. And then you can bond these parts to other things. This is so cool. I'm going to talk about these applications because now you can see where they're used. So has anybody ever heard of a GC or gas chromatography? Anybody ever heard of that? You've heard of it? No one else? This is so cool. What gas chromatography is if you let's see, if you have a tube, a spiral, let's say, tube. Okay, and if we look at it closely, if we expand on it, you have walls of the tube, right? So now if you have a gas molecule coming down this tube, it's going to bounce off the walls, right? If it's a big gas particle, it's going to take a little longer to go down the tube, right? Because temperature, it's related to temperature, 1/2 mv squared. So if it's a big particle, m is bigger, so the velocity is lower for big molecules. If you have a little molecule, it's going to go down this wall a lot, this tube a lot faster, right? Because m is small, so the velocity will be higher for the given temperature. So this is a key concept. Okay? If you make a gas that's mixed, that has heavy and light molecules in it, you make a gas go down a tube, okay? What do you think will happen when it comes out of the end of the tube? Will the light ones come out first or the heavy ones? The light ones are moving faster. So now you can spread out those molecules based on mass. If I measure when they come out, I know what molecules they are, at least what mass they are. So I create a spectrum, right? A spectra. So the light ones come out first, the medium weight ones second, and the heavy ones third. And if I put known stuff in there and do time of flight and all that, I can calibrate my gas chromatography tube. Okay? Now I need a pretty long tube to be able to spread these things out enough so I can measure the differences. So 3 meters is a good length. Well, look at this thing right here. This guy. This has a spiral in it. Okay? So here's an input and here's an output. Okay? And it has a spiral in there. And it connects the input and the output. And that spiral is 3 meters long. 3 meters, that's 9 feet. A little more than 9 feet, maybe close to 10 feet. Look how big this sucker is. It fits on a penny. Okay? So it used to be we'd need this big desktop machine, right? Thousands and thousands of dollars. Now they can make a gas chromatography pipe that is on top of a penny. So, and you need some LIGA type processes to make these things because you want the tube to be big enough so you can push enough gas through there, but you want it skinny, so you need it tall and skinny, that chamber, that tube. It's not really a tube, it's more of a, picture a maze, tall bushes on each side in a spiral. So it's tall and thin, so the molecules bounce a lot down the path. But it's tall enough so you can push enough gas through so you can detect things. Okay? So that's one example. This is really cool. You guys know what a heat exchanger is? What's a heat exchanger? What do we use that for?
Radiator in a car, for example.
Radiator in a car. So what do you do in a car? You have what flowing through the engine?
Coolant.
Coolant. So that's water mixed with what?
Antifreeze.
Antifreeze. Okay, so you have water going through the engine. So the engine has holes and pipes inside of it, right? Little gaps inside of it. Doesn't mix with your gasoline though. Okay. So you're pumping water through your engine block to keep it cool. Okay? So where does that water go after it comes out of the engine block?
Right into the radiator.
Into the radiator. And the radiator has little fins in it, right? So the water goes through the radiator and we blow air across the fins, right, to cool the fins down. So we cool the water. And then the cooler water goes back in the engine again and heats up. So that's a heat exchanger, a radiator. This is a 100 micron channel heat exchanger. So we've got channels that go back and forth like this inside of this thing, and then it comes out here. Okay, and I forgot they have some heat exchangers that Anka made that can do a kilowatt of heat exchange that are really small. They're 1 centimeter by 1 centimeter by 1 centimeter. And a kilowatt is like a space heater. If you buy one of those space heaters to heat part of a room that's kind of cold, they run from 1 to 2 kilowatts. It's a lot of heat, right? So this small thing could probably exchange about 1,000 watts. Okay, which is, 10 of the old light bulbs, the really hot ones. Okay, 50 of the CFC light bulbs, and what, about 1,000 LEDs. All right, gives you an idea. And then, of course, I mentioned microfluidics. You can see some microfluidic channels in here, right, going through here. So this is a polymer, and they use the stamp to make it. Yeah?
Do they use those heat exchangers for cooling of laptops and stuff?
I don't know what they use now. I know Intel bought some MEMS technology, some IP, because they were looking at how do I cool my chips. The ones that run a lot of computations in them, they'll get pretty hot. And that makes sense. It goes back to that experiment you did, R equals rho L over A. A is really small when you're inside of a computer chip, so you have high resistance. Even though the lengths are short, try to keep them short, they're still producing a lot of heat. So yes, you need to make heat exchangers, and one of the applications could be in semiconductor chip cooling. Absolutely. And then here's another type of, I think this is another heat exchanger, it looks like, of some sort. So you've got fluids coming in, or maybe multiple fluids. Maybe you do some kind of reaction here, and then this keeps it cool. It's kind of hard to tell sometimes what these things do. But you get the idea parts for. Okay, again, this is in gory detail. We use a substrate that's conductive, so we use titanium or titanium nickel, something like that, or an alloy. Okay, so we need to have something conductive. Then we put our PMMA on there, we expose the PMMA, and then we can use this conductive backing to do the electroforming. Okay, the photosensitive material is usually PMMA. Now when we do it in our simulation in lab class, we're going to use a different photosensitive material, okay, that's bonded to a steel backing. So you're actually going to do this in lab. You're going to simulate LIGA. This week, if the contact printer isn't up yet, I haven't gotten the status on it yet. Okay, so here in X-ray lithography, we used gold, which absorbs X-rays, and then we have the opening in the gold and the beryllium in the back, which is transparent to X-rays. We already talked. Okay, and then when we do it in the lab, we're going to use UV light to expose our simulated PMMA instead of X-rays. Okay, we use plastic, which is clear to light, and the black ink, which blocks the optical light. We use collimated X-rays. That's the key with LIGA, right? These are collimated X-rays. So that means they come in straight. So you don't have a depth of focus problem. They're extremely straight. That's why they use synchrotron radiation source. They come out collimated. Almost like a laser. Okay, it's not quite a laser, but the quality of the beam is like a laser. It's very, very well collimated, and you can actually have very precise frequency ranges, or you can have a broad frequency range of X-rays depending on the light. Okay, so this is a schematic of what happens at the end. Assuming you get some X-rays coming in, this is the beam line on the left. This comes out of the synchrotron radiation source. You have the beryllium windows. Okay. And then here's your beam on the end. And your mask sits right on top of the photoresist or the PMMA. And you scan the beam across. Of course, you have to cool everything because there's a hell of a lot of energy in these X-rays. And when they convert to heat, you're going to have problems keeping everything cool. Okay? And once you watch all the videos from Anka, this will do a job of explaining how you create these X-rays. So this is from a Shanghai synchrotron radiation source. Okay, they spent $175 million for this one light bulb. Now you laugh, right? That's a lot of money for a light bulb. TI looked at this when I was still working there. When was I working there? Late 80s, early 90s time frame. They were looking at building a synchrotron radiation source to power 20 X-ray lithography steppers in a fab. They were thinking about doing that. But they said the reason they didn't end up doing it is because they're relying on one light bulb to run an entire factory. If that one light bulb goes out, the whole factory stops. Now we have 40 steppers in a factory. If one stepper breaks, you still have 39 steppers running. But if you have a synchrotron radiation source that gives you 20 beam lines, X-ray beam lines, to run 20 X-ray lithography tools to make very, very small structures and high aspect ratio structures if you need those, then if that one light bulb goes out, you've got 20 machines that aren't running, so there's no output from your factory. So I think that's why TI kind of avoided going down that path 25 years ago. Okay, but in Shanghai they have a synchrotron radiation source, completed in 2009, cost about $200 million. And you can see it's circular, right? It's a big circle. Now they used a fisheye lens, so it looks a bit distorted, but this is the beam line right here, and it goes all the way around, comes back. So you get your electrons going in a circle at close to the speed of light. 2 to 3 giga electron volts. Very high energy electrons. And then if you just steer them a little bit in another direction, they give off light. How hard you steer them changes the frequency of the light. So if you make them bend even more, they give off more light, or they give off higher energy light. So the sharper the turn, the higher the energy, the shorter the wavelength. Okay? So you can control what frequency of light comes out of these things. When you do the lab, that's our light bulb. Okay? It'll actually be an ultraviolet LED-based flashlight that the forensics guys use. Works pretty well. We do a develop process, right? That's actually the developer recipe there. So if you ever want to make your own PMMA developer, that's one of the recipes you can use. You don't have to. When you do it in the class, you're going to develop it in water, which is kind of cool. You're going to go to the bathroom with a toothbrush and scrub it and clear the material off so you can expose it. Okay, then we're going to electroplate in the lab just like we. Okay, we're going to use a battery. We've got our source for metal will be copper. We're going to plate with copper. Okay? Same kind of thing we do with the PMMA. All right, I'm going to just kind of jump through this because we're going to go through this in detail. Posted so you can contrast the two. So now you had an overview of LIGA. We use different mask material because we have a different frequency of light. Just like in optics, if you're using ultraviolet, you're going to use calcium fluoride type optics instead, or quartz optics if it's near UV. If it's deep UV, use calcium fluoride optics. If it's visible, you'll use quartz or glass, regular glass. So, it just depends what you're looking at. Okay, you can use even plastics and things for visible light. Okay, so you use different materials depending on the wavelength of light that you're using in lithography, and you use a different process that allows you to get the high aspect ratios, and the process has to be working with the wavelength of light you use. So with LIGA, you're going to use PMMA or SU8. With optical lithography, you'll use photoresist. That's tuned for that frequency of light. Okay? So that gives you an idea of the differences between what we're going to simulate in the classroom and how they actually do it. Okay, so you have to do a plating process. Okay, and that's very similar for both. In fact, we have some electroplating equipment in our clean room that HT Micro uses and Todd uses for plating stuff. And he also can do it at his new fab now. You guys probably know that because you got to visit it. I haven't seen it. Okay, so well, we have our general disclaimer. Have any questions about that? About this stuff? Yeah.
I'm not sure about this X-ray source you're talking about. I mean, like, does Sandia do LIGA?
Sandia does LIGA on the West Coast. They have a synchrotron radiation source at their West Coast site.
So I mean, they built these accelerators, synchrotron accelerator LIGA process. Or
Mm-hmm.
therefore,
No, they use it. They use it for all sorts of things. So basically, when you watch the videos, they'll talk about how the synchrotron radiation source works. So you have a little ring where you accelerate electrons to a certain energy. Certain energy means a certain velocity. Okay, 1/2 mv squared. Right, that's kinetic energy of the electron. How do you accelerate an electron?
Magnetic fields.
No, that's how you steer an electron. If an electron is still, it's a really good comment you made. If an electron is still in a magnetic field, it feels no force. Okay, so the force on an electron due to a magnetic field is some constant, okay, times the electric charge times its velocity. It's a cross product. Magnetic field, yeah. Q. Okay, let me write this again. It looks like crap. QB cross V, and B is a vector, and so is V. So when you take physics down the road, or if you go back and do engineering later, or decide you want to be a physicist, God forbid, and you'll be like Camby's and I, we're physicists, you'll find out that it's the cross product of the vectors, so it's a right-hand rule thing. Okay, so if my magnetic field is going into the page, so we're seeing the tail arrows of our vectors, which you can think of as arrows, right? You see the feathers, right? It's going into the page. Does that make sense? If my electron is here, it feels no force. If my electron's moving in that direction, V, then you go V cross B. So I'm going from left to right, okay, with my V, and my B is going into the page. So V cross B is a right-hand rule. So if you take your right hand and you take, okay, the direction of the velocity vector, and you cross it, so you do a right-hand rule, you cross it with the direction of B, and B is perpendicular to it. The cross product, or the right-hand rule, the thumb tells you which direction is the force. So the force, okay, is going to be in this direction, right? It's at the right angle to those two. So the electron's going to turn, isn't it? Well, now it's going in this direction, and the force is going to be at right angles to it again. Right? That's supposed to be a right angle, so it's going to turn. What trajectory is this going to have? It's going to be a circle. Okay, so that's what happens inside of a deep reactive ion etcher. Can someone open the door for April, please? Oh, she's got it. Hi.
Hi, here.
Here. Oh, you found some notebooks. Very nice. Thank you. So, so with a magnetic field, you can get an electron to go in a circle. That happens inside of a high-density deep reactive ion etcher. They put a magnetic field in there to keep those electrons, those ions, going in a circle, rather than hitting the side of the chamber and losing their energy. Okay, so you can use magnetic fields to steer things. All right, but how do you accelerate an electron? How do you make it go faster? We can steer it with a magnetic field.
Heat it up.
Yeah, not quite.
Electricity.
You're close. What happens in an with electricity? In a wire, how do you make an electron move?
Put a charge on it.
Put a charge on it, or how do you get an electron to move in a wire? What do you add to it?
Voltage.
A voltage. Exactly, a voltage, right? V. So if I have positive, here, let me get another plate here. So that's how they get it to accelerate, is by putting a large voltage, right? So they have little voltages all along here, and the difference between each one of these plates is a certain amount of voltage. So each one of these kicks that electron up to faster and faster speeds, higher and higher energies. So they get these guys going in a circle, right? They bend them with magnets, and then they accelerate them with voltages. So they go really fast, and then they enter the big ring, the storage ring they call it, and they continue accelerating it. So they go to 2 to 3 giga electron volts. That's a G, giga electron volts. And if you do the math, right, 1/2 mv squared, you find the m of an electron equal to 3 giga electron volts. You can determine the velocities very close to the speed of light. They're freaking going fast, really fast. So they're really, really, really fast. And then they're not in a perfect circle, because if we put some magnets here and make it bend a little bit differently, you're going to change the direction. It's going to give off some energy when you do that. You make a sharp turn. And that is the light coming off of it. So they'll have beam lines coming off of this thing. And by bending the electrons different ways, they can get different frequencies of light coming out of each beam line. Okay, so when you go through the LIGA unit, you're going to read and you're going to see a bunch of videos, and they talk about different beam lines. They have a far infrared beam line, which means they just bend it a little bit, and they get very long wavelength light. And then they have high energy X-rays beam line, where they really make those electrons take a sharp turn. They get higher energy photons coming out of it in the X-ray spectrum. And they use that for lithography. They also use that for X-ray diffraction, crystallography, determining the crystal structure of different materials. So there's some short videos on that. So it's pretty cool. You have one light bulb that can give you any frequency of light you want. That's why they spent
So
$200 million.
how do they guide the light from that accelerator, the synchrotron accelerator to
It comes off straight.
little?
If you have to, when you do the bend, there's a point where the electrons give off the light in a certain direction.
So what's the radius of the circle?
A couple 100 meters usually. 2 football fields. Or as they say, 2 soccer pitches. Okay? So you have a light bulb that can give you any frequency of light you want, just by playing with those electrons, which is really cool. You know, and X-rays are a lot of fun to work with, because you can see really small things and you can pattern really small things. And there's always a drive to making things very, very small.
I have a question, sorry if my lack of knowledge. Why don't they just use an X-ray source like the doctor's office dentist's office that uses X-ray.
It's not collimated.
Oh, okay.
And those X-rays spread out, so you don't get any depth of focus.
Okay.
H line and an I line on a C and
On a mercury arc lamp, that's a mercury arc lamp. The G, H, and I lines are different frequencies of light. Okay, so if you look at the spectrum, you have your I line, you have your G line, and then, no, H line, and then you have your G line. This is like green, this is like blue, and this is near ultraviolet, 365 nanometers. So the smaller the wavelength, the smaller structures you can pattern. So X-rays are down, I don't know how many nanometers, but it's low, very low. Extreme X-rays are probably a few nanometers or less.
90,
same
I
as
think.
UV.
It's past deep UV.
Very-
It's the same in that they're all photons, right? But as the wavelengths get shorter, the photon energy goes up. So each photon carries more energy, has a lower frequency, lower wavelength,
It's the size
higher
of atom.
frequency. So X-rays will interact with the electrons in an atom really well. They'll kick things out. You know, they do X-ray fluorescence. Okay, so they excite an atom with X-rays, and then they look at the electrons going back into the lower shells again, and when they do that, they give off light, or they give off X-rays of different frequencies. And they'll look at that spectrum, and then they can figure out what materials that they're hitting them with. So there's lots of things you can do with X-rays. You can probe things, you can pattern things. You know, in this case, but with LIGA, we're just talking about patterning. So go through the, unit, watch all the videos, watch them a few times. I'm going to post the reading and the assignments. There'll be a crossword puzzle, oh joy. And there'll be a research project where you have to answer some questions and go online and look for stuff about LIGA. Or get it from the videos. So, and yeah, you should probably try to look at HT Micro's site too, if you're thinking about getting a job there someday. I should probably try to get Todd to come in and talk about LIGA, but he's so damn busy, I don't think I'll be able to get him. So, anyway, that's about it. Any other questions? Is it time to go?
Just about.
Next class.
Till your next class? Yeah, so if I have two plates, right, this is positive and a negative voltage, and I put an electron in the middle of it, which way is it going to go? No, it's got a negative charge. It's going to go this way, right? Opposites attract. Okay, so if I have a really big voltage difference, it's going to go faster, right? It's going to feel a bigger force, right? So that's how they get these things to